welcome. This is the first of the Conservancy's four-part speaker series that we plan over the next 2 years. It's part of our 25th anniversary celebration, and we're hosting this series of events on topics that we hear about all the time as we talk to people that are members of the Conservancy. Things that concern them, things that we're looking at as the long-term future concerns. I want to thank our 25th anniversary sponsors right out of the gate, Northwestern Bank and Idle Farms, as well as the speakers, panelists. We're so happy to have everybody here today. It's hard to be inside on a day this beautiful. Each of our speaker series programs is going to focus, like I said, on topics of vital interest to the residents of leelanau County. And we want to see our local concerns and how our own observations of what's going on in the environment, how we can put them in the context of a rapidly changing world. So our speakers are primarily going to be scientists, people who have spent a life trying to understand the natural world and the impacts that we see every day. And they'll be able to shed a certain light, from their research experiences and help us to understand our place. So this fall, the topic is going to be agriculture and food system. Next spring, we're going to look at forest ecology, and changing habitats. Pat Doran, we may invite you back. Finally, we want to take a look at our communities, how they're changing, demographics, and the way people live today and how that impacts the way we interact with the environment. But today's topic is water and the future of the Great Lakes. The Conservancy is interested in this topic because the health of our watersheds affects all the work that we do. It's of vital interest to our members, has been for a long time. It's one of the reasons the Conservancy has been working with lake associations, doing water monitoring since 1990. It's a long-term effort on our part. So our first speaker, Dr. Patrick J. Doran, is currently Director of Conservation for the Nature Conservancy in Michigan. He oversees the Nature Conservancy's conservation efforts, including the organization's conservation science, restoration, protection, and policy activities, not only for Michigan, but also for the benefit of the Great Lakes region. Patrick previously served 7 years as Director of Science for TNC in Michigan, and he holds an appointment as an adjunct assistant professor in the Department of Fisheries and Wildlife at MSU. Dr. Doran holds a PhD in ecology from Dartmouth College and a master's degree in ecology and environmental science from Indiana University. Pat, you're up.
Is my mic on? Can everybody hear me okay? Great. Well, thank you so much. It's a pleasure to come up today, and thanks to you and the staff and your board. I'd love to come out and talk, so anytime I'd be happy to drive back up. So let me get to my first slide. So I want to talk to you today and just kind of tell you some stories about the Great Lakes. I'm going to mention some of the conservation issues in the Great Lakes. I'm going to have hit on some themes about climate change, but I'm also going to tell you about some of the conservation actions that we can take. And when I talk about conservation actions, I talk from our very traditional and long history of land protection that all the conservancies do around the country, to the stewardship and restoration of that land, as well as partners' lands, and then up into the policy impacts that we can have that also change and alter land and water management throughout the country. All right, so I'd like to start with this slide just to put things into perspective. This is the globe, this is Earth, and we have a big blue marble there that is all the water on Earth. All the water in the oceans, in the ground, in you, in your dog, in your orange juice. All the water in the Earth is there. That's a sphere about 800 miles. It goes from, I think, Salt Lake City to about Topeka, Kansas. That's all the water in the world. This next little one is about 150 miles. That's all the fresh water in the world. 99% of that fresh water is groundwater, which we don't have access to. And that's sitting over Kentucky. Now there's another dot on the map. Does anyone see that one? Right here about Atlanta, Georgia. That's a sphere that's about 30 miles. That's all the water in the lakes and rivers in the world. right? It looks smaller than Lake Michigan, but on average, Lake Michigan is not that deep. This is a sphere that's 37 miles high. But that puts in perspective what we're talking about. And when we can turn around and look out our windows here, and that takes up a big portion of that sphere. So we are in the center of the world for that accessible water. We have a vital resource here, and we need to conserve it and we need to protect it. Excuse me for a second. So I always start to talk about thinking, what do we care about? And I was reading your brochure over there, and I really like, you have a statement in there about touching lives and protecting land. When I think about why we care and why we are in the business we are, I think about the concept of ecosystem services. I'm a scientist. We like to classify things. The topic of ecosystem services in the literature is really blossoming over the past decade. And we tend to think of provisioning services and regulating services, right? We regulate climate and clean water and air. We have cultural services like our spiritual, our sense of recreation, our sense of place that we have. And we have our supporting services like photosynthesis, right? And those are all very nice, but we can see what they really mean to. I just put some stars on here to the things that are connected to water. There's more. This was just me up late the other night before I gave a different presentation. But these are the ones that are connected to the water. These are the ones that are relevant. And I think what's interesting is I can kind of look at this slide from a science perspective, and someone over there looks at it from a different perspective, and somebody over there looks at it from a different perspective. I gave a talk to a Dow Corporation the other day, and they see a whole lot of different things in this slide that I tend not to see. But I think everybody can find the things that they care about somewhere in this slide. So what's the issue? So first I want to back up. I don't mean to do a commercial for the Nature Conservancy, but there are organizations like ours, like the Leelanau Conservancy and the Nature Conservancy. We work globally to work on the lands and waters. You work locally in this region to work on those lands and waters. We want to see collectively, we as a society want to see a sustainable world for future generations. So what are we talking about in the Great Lakes region or in Michigan that we really work on? What are the major system types? Well, we have watersheds, our agricultural watersheds in the southern portions of Michigan, southern portions of the Great Lakes. We have our northern forests, the great kidneys that give us all the clean water and the clean air and support biodiversity, as well as support industry and the towns and municipalities. We have our coastal and nearshore areas, more coast in the Great Lakes than all the Atlantic seaboard. We have our aquatic food web that supports life out in those lakes. And we have kind of two major drivers, two major threats that that the Nature Conservancy tends to focus on. One is aquatic invasive species and climate change adaptation. I'm going to try to drill through all these things, but these to me, and where I work, tend to be the reflection of that slide that I just showed you. So what's the problem? This is a map of cumulative impacts, cumulative stress to the Great Lakes. This was a scientific exercise that I was privileged to work on with the University of Michigan, as well as over 20 different researchers around the Great Lakes from academic institutions. What we tried to do was look at 20 plus different stressors to the system. We looked at toxins, we looked at environmental contaminants, we looked at climate change, we looked at aquatic invasive species, we looked at human population density. All a number of things that influence the health of the Great Lakes. And we kind of mapped them all together. We had a spatial data layer of each of them, and we actually added them all together, and we developed a map of cumulative stress, where the red areas are much more higher stress than the blue areas, okay? Now you see the coastal areas that we care about. Well, you know what? That's where all the stress is concentrated. And not only this, another thing we got to do was look at some of the values that people care about. We looked at just a couple things like beaches that people visited, marinas, places to go bird watching, and all those things that people care about, they're in the reddest most areas. So not only do we see a lot of high stress to the Great Lakes system, but the things that we much care about are in those high stress areas. So that's the threat, that's the impact, that's the things we have to worry about. So we also got to work on a project that was a whole conservation plan for all of Lake Michigan. We also did another one for Lake Erie and Lake Huron and Lake Ontario. But again, I just want to indicate the things we really care about. This is a map of Coastal wetland is the biodiversity significance of coastal wetlands. This just looks at the biodiversity importance. But you see, all these high biodiversity areas, the greenest most areas up here, these are regions and areas of high coastal wetland biodiversity. Up here, leelanau Peninsula, you have some high areas and some kind of medium important areas and some lesser important areas for wetland biodiversity. That's when you look at a whole lake scale. And again, over here, we have condition of those wetlands. So this kind of is a reflection of that map that I just showed you for the whole Great Lakes. These ones up here in high, pretty good condition, kind of medium condition. These tend to have poor condition, actually over in Green Bay where I cut those guys off because they play for the Packers, I think. And this one is, I'm sorry, I got that backwards. That first one was the coastal terrestrial systems, like the dune side of the system. And this one is of the coastal wetlands and the biodiversity significance of the coastal wetlands. But I just wanted to show you those two maps again to show you what do we value, where's the biodiversity we value, where is the cultural asset we value, the scenic assets we value. And they are, in not necessarily always, but some of these areas are in pretty poor condition. This is just a simple map that somebody put together the other day, and this is, again, some of the land conservation that my organization has done over time. But what's really nice about this is you see this high concentration of areas that my organization is based on in coastal areas. Up here in the Lake Cheneau area, all the way down the eastern shore of Lake Michigan, all along northern Lake Superior. We are invested in these assets, and we collectively, not just the map that I'm showing here, but all of our conservation work collectively is focused on these coastal assets. And we must think about the health of them, not just for today and tomorrow, but the health of them 100 years into the future, 200 years in the future. So what does that future look like? So I'm going to show you a couple climate change slides here. And this is an interesting graphic to me because basically it is saying the Michigan of the future in the mid to end century, we're going to experience a climate that is similar to this part of the country. So this is kind of mid and end century, and the red and the orange are different climate scenarios, one with more carbon or more emissions in the scenario and one with less emissions in the scenario. But that really doesn't matter. What's interesting here is we projected to experience a climate that is more like this part of the country than this part of the country. So what are the actions that we must take today to be able to adapt to that kind of change? So these are some projections here, just some of the variables that might change. Expected to be warmer by at least 1.8 degrees, 2 degrees. And there's some variables, warmer winter nights, more intensive weather events, more intense rain events, especially in the springs of the year. More precipitation, likely in winter months or late winter months, and likely as rain. And as you know, our lakes are tending to get warmer and less ice, which means more evapotranspiration, which means lower lake levels. So we expect to see these things. I'm not certain that we're going to see these things. I don't know for certain. These are models. These are projections in the future. But they're evidence-based. They're science-based projections, and they're the best we have. But what I do know, before I go a little further, I just kind of want to do a little bit of take-homes on some climate change thing, because there's a lot of words and there's a lot of jargon out there that I want to be clear. One is the idea of mitigation versus adaptation. Have people heard these two words? Mitigation tends to be efforts to reduce the buildup of greenhouse gases in the atmosphere and slow the rate of climate change. This is where you hear things about going to alternative energy, or you hear policy things like cap and trade. I don't want to get into those things. I prefer to stay away from them. But they're all geared at having less emissions to slow the rate of climate change. And then we have the concept of adaptations. These are adjustments in either human behavior or natural systems that promote persistence or function in light of change. So what are the things that we can do knowing that change is coming and that change occurs? So I want to be very clear on those two things. I'm going to talk mostly about climate change adaptation type things. Another thing I want to be clear about is the weather versus climate, right? And we oftentimes hear these debates, oh, it's snowing, therefore there's no climate change, it snowed in May or something like that. Weather is day-to-day fluctuations that tend to be somewhat unpredictable beyond a couple of years or beyond a couple of days. Climate is the long-term statistical average of those variations and those changes. So I oftentimes think about it is weather determines what clothes I tend to wear today. Climate determines what clothes I have in my wardrobe, right? If I live in Michigan, I have different clothes in my wardrobe than if I lived in Florida. So that's how I always remember it. So, the famous philosopher here, Richard Dawson, We did a survey it's about a year or two ago of Great Lakes coastal managers all around the Great Lakes. We did a survey of 500 people. These people that work for federal governments or state governments or land conservancies or municipalities, scientists. And people understand and are thinking about climate change in their management. So if I go to a conservancy around Michigan, most of our land managers or our protection people or staff, they know they should be thinking about climate change. Climate change is on their minds. 80% of our respondents know they should be thinking about climate change. But about half of them are a bit confused about the science. They don't necessarily understand the mechanisms. They don't necessarily understand, they might see the changes but not be clear on why there's certain changes. But what scares me is that only about a quarter of people know what to do in response to those changes. So think about that. That's a huge gap. 80% of the people are thinking about it and are aware of it, but only 25% know what to do. That scares me in my job, right? I want to see that number be about 100% to know, and I want that number to be about 100%. Even if they're not going to do anything, I want people to know what they should do in case they do see some changes. So, I want to give you a few reminders about what are we adapting to in some of these systems that we care about, our forests, our watersheds, our coastal systems. What are the impacts that we're tending to see that we've been seeing in the past already and they're projected to see in the future? So in forests, we expect to see temperature increases. That has drought stress on the species that we're trying to manage for, whether we're managing to cut them or we're managing a nature preserve. Our disturbance regime, things like fires, might be more intense and more frequent if we have a drier system. And we also can have more pests and pathogens because winter times might be less cold and pests and pathogens might be able to survive longer, or they might be able to introduce to a warmer environment. For our watersheds, kind of these agriculturally dominated watersheds in the southern parts of the Great Lakes, we're going to see some increase in intensity of precipitation. Well, with that comes in the springs of the year, like this year, we tend to see more runoff, more sedimentation from those areas, more nutrient addition to the areas, and we end up with things like large algal blooms in the western basin of Lake Erie. We might see increases in temperatures there and a high potential for maladaptation. So in southern Michigan, I got just a graph from the other day from the Department of Environmental Quality that is showing the increase in requests to put in groundwater wells, and most of those are to irrigate in agriculture. So over the past maybe like 5, 6, 7 years, that increase has gone way up. And we're seeing requests for irrigation in Michigan that you only saw when you went out into kind of the central part of the U.S. You're seeing central pivot irrigation that we didn't see that much. And you're seeing many farmers investing in that type of irrigation because the fluctuations in intense rainfalls or drier late summers are getting wilder and more unpredictable. In our coastal systems, you're going to see all these things, but you see increasing water temperatures, increasing eutrophication, which is the warming of our lakes, increasing toxicity, decreasing lake levels through that evapotranspiration, and positive feedbacks with that ice reduction. And all these things might lead to lower lake levels in some years and higher lake levels in other years, depending upon situations. So we have to be able to think about all these impacts when we manage our natural resources, manage our natural assets, or when we use them. So here's the problem that I think about pretty much every day in the work that I do as a conservation practitioner. Within the Great Lakes region, observed and projected rates of climate change pose a major challenge to natural resource managers, us, policymakers, and conservation practitioners as they strive to restore and maintain biological diversity and protect the systems that we care about. Our conservation work simply cannot rely upon the assumption of a stable climate. We can't. We can't think that lake levels are always going to be the same or within a nice narrow range that is good for our properties. They don't. Lake levels don't do that over the long term. We can't think that temperatures are going to be the same, or there's going to be the same amount of rain, or that spring is going to be the same day every year. We just simply can't do that, and we need to manage our systems to be able to handle that variation. When I first studied ecology, ecology is the study of variation. We need to embrace that variation. So, two major philosophers. Does anyone know who this is? Oh, I thought your hand was up. Who is this? This is the only thing I remember from College Philosophy 101. This is Heraclitus. Anyone? Heraclitus. And what did Heraclitus say? He said, everything changes and nothing remains the same, and you cannot step twice into the same stream. This is a long time ago, a few thousand years ago. Who's this guy? David Bowie. Don't you feel bad that you recognize this one and not that one? Please don't tell your parents. And what did David Bowie said? I watched the ripples change their size, but never leave the stream. Thousands of years apart, these two people are telling us from a philosophical, everything changes, you better be able to handle it, people. But we get in our own comfort zone, and we don't handle that change very well. So, what are we going to do? Right? We've got some crazy projections about what the future might look like. It doesn't necessarily look like it is today. We have philosophers been telling us for 2,000 or 3,000 years that we better accept change. We have confusing systems and graphs. We have people that aren't sure what to do. So hopefully I'm going to tell you everything we need to do. Maybe I'll hint at a few things. I can't tell everything. So one thing we did do, as I mentioned earlier, I showed you that graph. We have at our disposal biodiversity conservation plans for all the major lake basins. This is an effort that the Nature Conservancy was part of. The EPA funded. This was through the Great Lakes Restoration Initiative, the influx of money. And we were able to convene hundreds of partner organizations like the Leelanau Conservancy here and other partner organizations around each of these lakes to say, what are we going to do about biological diversity? We have another one that's drafting for Lake Superior. So what do these things tend to say? Well, we start to address things like low lake levels. And you see this all over the place, right? You can't go to a paper, or you can't go a week without reading something about low lake levels or in the news or hearing on the radio as I drove up this morning. Drier summers, this is last fall, October of 2012. Drier summers pushed Lake Michigan to low lake levels. This was in the Detroit paper just about 2 or 3 weeks ago. Michigan coastal communities could lose millions because of those low lake levels. Great Lakes levels up slightly, but boaters are going to be shocked when they get there. This was March 1st. And this one was in the National Geographic online. Low lake levels. And this is my favorite part. Don't fight nature, plan for it. We have to understand that low lake levels are not out of the realm. They happen, and we have to plan for it, both plan on the nature side of it as well as our human recreation infrastructure side of it. So I want to give you an example of some low lake level ideas, how we account for low lake levels, and some ideas about what we can do about low lake levels, both in terms of the management of lake levels as well as the management of our natural resources in light of those. So it's a multi-sector problem, right? And some of you are probably looking at this graph and you can probably see yourself in at least a couple of these circles. So lake levels influence ecosystems. This is where I work. They influence the coastal zone, the municipalities and the towns that live on those coasts. They influence the recreational boating and tourism industry, hydroelectric generation, navigation. We have to think about all these players as we go about managing lake levels, right? We can manage lake levels at two places, at the end of Lake Ontario and at the end of Lake Superior. That's about it. So the International Joint Commission, who some of you might have seen some news with recently, came out with a report and recommendations about lake level management. What I really like what they did is they went to each of those sectors that I mentioned. You don't have to read all this, but they went to every single sector that I just mentioned, those 6 sectors, and they said, why are you vulnerable to low lake levels? Why do you care? And so you could go to the top, the domestic and municipal water users, and say the impacts at extreme water levels, either very high or very low, can include unusable and compromised water intakes, sedimentation problems for those intakes, increased operations and maintenance requirements, and reductions in water quality. That influences that sector of society. If I come down to the ecosystems where I work, natural fluctuations in water levels over both the short and long time are essential to actually maintaining habitat diversity. We need fluctuations for our coastal wetlands and our bluffs and dunes. But coastal protected and riverine wetlands, beaches, and dune systems, tributary connections in their estuaries, and other coastal margin environments are particularly sensitive to fluctuations in lake levels. One issue is over in Georgian Bay, where if lake levels go down, there aren't wetlands, there are waterfalls, because there's a nice rocky Niagara escarpment there. So what I like what the International Joint Commission is, they said, well, they went to each of these sectors and asked, tell us what a coping zone is. And I like this concept of a coping zone because it really works for me because I have small kids and I think about their coping zone. When do you feel okay and when do you start to get uncomfortable? So after about 9 o'clock, my kids are outside of their coping zone, or actually I'm outside of my coping zone with them, right? But about 8 o'clock, things are starting to get in a danger zone. About 9 o'clock, it's like, all right, get to bed. You've got me outside of my coping zone. I like this concept because I can go to the navigation industry, not me personally, but we can go to the navigation industry And they could say, you know what, if lake levels are around this range, and these are real ranges, 183 meters above sea level, they can go full bore on their operations. If things get down to lower zones, they have to start light loading. They can't carry as much cargo. If they get down here, they can't even access some ports. So this is a danger zone for them. And the same thing at some high lake levels. They have problems accessing ports. I could go over here to the environmental and think about my coastal wetlands. And remember what I just told you? If lake levels always stay the same, our coastal wetlands don't do so well because they need a little bit of disturbance. They actually are happy when there's a little bit of disturbance. If lake levels get too low, those can stay there for years. Those coastal wetlands dry up and lose species and lose habitat. If they get too high, they get drowned out. And again, we might lose species. But what I like about this is you can go to each sector and you could probably find some sweet spots in the middle of this graph. And then if lake levels get too low and are sustained at some point, we can kick in a different regulatory mechanism, a different management regime at the outflow of Lake Superior and let some more water through. So the International Joint Commission in this exercise came out with some very important regulation recommendations. They thought about climate in those recommendations. They made projections in the future about what might happen to lake levels, which is a good thing. They thought about the benefits to ecosystems, not just the benefits just to Lake Superior and just the boats in Lake Superior. They thought about benefits to the whole system and included all those different sectors and included the ecosystem impacts. Again, they thought about multiple considerations for multiple sectors, and it's adaptive across the whole Great Lakes system. They can alter that as opposed to, oops, sorry, is that for me? No. But what do we do? That's kind of at a regional level, at a whole Great Lakes system level. Well, my organization, we own a coastal marsh called Erie Marsh down in western Lake Erie, just north of Toledo, and we have about 1,000 acres of diked wetland there. It's kind of getting a bit old, and we were able to secure some funding to upgrade the dike system, as well as upgrade a pump that pumps water in and out of the dikes. If you've ever been in National Wildlife Refuge, they have different components of their wetland system, and they move water in and out seasonally depending upon fish or the birds they like to attract. And we also put in fish passage where there wasn't fish passage before. So we've actually put in fish passage to give fish access to another 900 acres of wetland for spawning habitat that did not exist. Really cool coastal restoration, and we're really proud of it. But one thing we had to do there is think about lake levels when we did that restoration and when we put in that infrastructure. We're making big investments. If we were ignorant of future lake levels, we might put in a fish passage structure or a pump to pump water that's going to have big intake problems in the future, or when lake levels are really at a sustained low level. We can't have them too high either. So we had to think about in our restoration work accommodating for any of those future scenarios, whether it's decisions about which species to plant there in our restorations, whether it's decisions about where to do those protected areas and what might be there in the future. We have to think about things for invasive species. Right now, there's a whole lot of habitat all throughout Grand Traverse Bay here for Phragmites. A whole bunch of new habitat that wasn't there about 2 years ago. So we have to think about, is that new habitat for invasive species, which are oftentimes ecologically very quick colonizers or very quick spreaders and very quick growers? If that's the case, then we need to think about things like early detection programs, rapid response programs. We need to be cooperative. We're involved in a partnership, the Michigan Dune Alliance, up and down the whole coast of Lake Michigan. And together, a suite of organizations and agencies, both federal and nonprofit, are working together to do early detection of invasive species and a rapid, quick response to the eradication of some of those invasive species. We have to think about that more for some new areas, perhaps, and for some new species, and we can only do it with collaborations amongst different organizations. I can't go out and do it myself, and you can't go out and do it yourself. Now, what's interesting to me is we can do that kind of from the ground up, right? We can do it from a grassroots effort of organizations just deciding to get together, but we also have to facilitate that type of work at either a state level or a regional level with the right types of policies, with the right types of resources, with the right types of data information and data sharing, and that type of thing. Another thing I think about when I think about lake levels changing in coastal infrastructure is there are parts of the country that deal with ocean level changes from the tides on a daily cycle. And they have the infrastructure to be able to handle that. It doesn't work everywhere, but we have to think about this might be opportunities for us to invest in the future in infrastructure in our coastal systems that is much more adaptable. Instead of some really hardened shoreline, we might be able to move to some more softened or natural or nature-based shoreline. That doesn't work everywhere, and I'm not saying replace every piece of hardened shoreline with natural shoreline, but both of those things have to be part of the equation, part of a solution. But what's important here is we also have to think about the economic impacts of those. I'm always fascinated by, I've heard this stat, I don't know if it's exactly true, but in the Great Lakes, the Army Corps of Engineers spends most of its dredging, and I heard about 50% of their dredging money in the Toledo Harbor. So half of the money they spend in the Great Lakes goes into that one place. Well, you know where that problem's coming from? It's coming from the Maumee River Basin that's like 90% agricultural. Can we think about a different way to spend that money? Instead of spending it there, can we spend it in practices or wetland restorations or practices to keep that soil on the land instead of spending it down out in western Lake Erie? I don't know, but that's the kind of solution we have to think about, or else we're going to be spending that millions of dollars every year for the next 100 years. We have to think about all different alternative solutions. And you know what? Climate change tells us there's going to be more precipitation, so you might have to do more dredging just to stay even, just to stay at the same place. So, I think this is my last couple slides. And generally, we want to promote these things. We want to get the values from the systems, and we want to see our natural infrastructure, the nature, our protected areas, our recreation areas, promote those types of things. Potentially, we want to avoid things like hardened structure that don't allow for that type of change, don't allow for that dynamic nature of that change over decades, over hundreds of years. And we hope to avoid problems like this that are not so uncommon in some of the bays around the Great Lakes. Here you can find a little bit more about the work I talked, but that's all I have, and I think I'm going to hand it back over to Tom and Brad, and we'll be able to take questions for you. So please write down some good questions on those note cards, and I can answer other questions too. I had other slides on some of the agricultural work that various organizations doing around the Great Lakes Basin to also abate some of these impacts to these systems as well. Thank you.
Thanks. Thanks, Paul. Our next speaker is Tom Nalepa. He's a research biologist with the Great Lakes Environmental Research Lab, otherwise known as GLERL, which is part of the National Oceanic and Atmospheric Administration, which is known as NOAA. Lab's based in Ann Arbor. He was there 37 years before retiring from the federal service in 2011. He's now part-time faculty member with the Graham Institute of Environmental Sustainability at the U of M, and also maintains emeritus position with NOAA. Tom's research focuses on understanding changes in the structure, function, and health of lake bottom ecological communities in response to a variety of factors, including invasive species. Nalepa is best known for his seminal work on invasive mussels, including zebra and quagga mussels, and their effects on Great Lakes communities. He's published over 100 papers on Great Lakes issues. If you Google his name, you probably can see about 50 of those papers listed, but you can't read them because they're all in scholarly journals that you have to subscribe to. But Jeff Smith is here, and he wrote a great article that's in MyNorth, right? MyNorth.com. And you should read that about Tom and his research, and maybe he'll talk a little bit about that.
Well, thanks for having me. It's great of you to come on such a beautiful day, and it's a pleasure to talk about something that's really true to me, is talking about how invasive species have affected the Great Lakes. There's all kinds of multiple stressors out there, and Patrick talked about quite a few of them. And what I'm going to do is focus mostly on invasive species. primarily the Dreissenid mussels, and what impacts they've had on the food web and the ecology of the Great Lakes. Because I contend that over the past 10 to 15 years, there's not a single aspect of the Great Lakes, when you look out in Lake Michigan or Grand Traverse Bay, on how the intricate food web and the connections between the physical, the biological, and the chemical variables, that not a single aspect has not been affected one way or another by what the mussels have done. And many of you probably don't see mussels anymore. When you take out your boats and your docks, do you see any mussels anymore? Maybe not. But believe me, they're out there in Lake Michigan, and I'll show you some slides of what it looks like when you go out in the middle of Lake Michigan. There's like Patrick mentioned, there's all kinds of stressors out in the Great Lakes, and although invasive species are just one stressor, they kind of interact with all the rest of them to compound the problem or exacerbate the problem or make it more complicated to try and figure out what that individual stressor is doing, because invasive species are now in the middle complicating the whole picture. This is just a slide of the cumulative number of invasive species in the Great Lakes. And it's not anything new. You can see over time, ever since the records were kept in the mid-1800s, that the number of invasives has basically gone up almost exponentially. The first record is the sea lamprey in 1835, and I think it's kind of ironic that the sea lamprey is still with us. We're still fighting it. And of all these 184 non-indigenous or invading species, I've read it, I don't know if anybody's checked or not, that they're all still with us. We haven't been able to get rid of them. And here is the sea lamprey in 1835, and we're still fighting it. The last record is the bloody red shrimp, Hemimysis. It was found in 2006. And so if you think about it, there's no new invader in the Great Lakes since 2006. And we were talking with Carolyn and Zane beforehand about how a lot of people don't like coming to these presentations about the Great Lakes because it's so depressing. Well, this is a bit of good news, isn't it? We haven't had a new invader since 2006. Well, unfortunately, the rest of my talk is going to be depressing. So hang on. So in theory, 1 out of 10 of those species that is introduced into the Great Lakes actually becomes established. So multiply 10 times 184, that's how many have been introduced. We've had the Chinese mitten crab, we've had the European flounder. Those species have been introduced, but they never became established. These are species that are established and reproducing. Whoops, go back here. Here's a shot of all 184 of them. In a half hour, I won't have time to talk about each one of them. But the poster is available. You can download it on the NOAA GLERL website. When you break it down, 61 of those are plants, 52 invertebrates, 26 fish, 26 algae, 19 bacteria. That includes fungus and viruses. The trend is for more plants early and more invertebrates now, presently, over the past 20 to 30 years. These are invertebrates that live both in the water and occur in the bottom sediments. And the mussels, of course, are invertebrates, and they occur on the bottom. How did they get in? What is the vector for these species getting in? Canals, deliberate release, or this is stocking. A lot of them are unknown. But when you look at the trend, what jumps out at you immediately? Shipping. Ever since 1960, the shipping vector has jumped, the percentage of species getting in via the shipping vector has jumped pretty dramatically. So since 1963, 63% of those species that have become established in the Great Lakes were introduced via the shipping industry. And what happened in 1959? right? You know? St. Lawrence Seaway was open. This is the same slide. You can see almost not only has the vector changed with more of a shipping, but the rate seems to have increased as well. So what happens? The ships, we opened the Great Lakes to ships from around the world. They come in with ballast water, and when they have freshwater ballast, they come into the Great Lakes to pick up cargo. They dump their freshwater ballast along with all the organisms that they picked up overseas, dump them into the Great Lakes, and if the conditions are right, they survive and start reproducing. The outrage of the public from all these species that got in through the shipping industry in the 1980s, we got the fishhook water flea, the spiny water flea, we got the rough, we got the goby, we got zebra mussels, we got quagga mussels. All these came in between about 1984 and 1990. People were outraged, and as a result of that, the Aquatic Nuisance Prevention and Control Act was passed in 1990. And what that Control Act said, all ships coming in to the Great Lakes with freshwater ballast must exchange their ballast water in the open ocean beyond the economic zone, which is about 200 miles. So they must dump out their fresh water, pick up salt water, and then come into the Great Lakes. And the Coast Guard was charged in making sure that that ballast water was salt, not fresh. But we still, if you look at that graph, even though they were doing that in 1993, we were still getting invasive species coming in. What was happening is species were coming in ships that weren't carrying ballast water. They were carrying cargo. So they didn't have ballast water tanks, but they had sediments in the bottom of their ballast tanks. And what was happening is they would come up into the Great Lakes with cargo and all this sediment in their tanks, and they declared, I don't have any ballast on board. So when they bring in a load of steel to Cleveland, say for instance, and they drop off that steel and they go up to Duluth to pick up grain, when they put in freshwater ballast, it mixes the sediments up, and all the organisms in these sediments would then be discharged when they picked up the grain in Duluth. So as of 2006 then, what we call no-bobs, no ships without ballast, were regulated as well. So 2006 is the key, and we haven't had a new species come into the Great Lakes, at least through the shipping vector, that we know of since then. Now, not all of these 184 species are considered nuisance species. Probably most of them you wouldn't even know that they're there. In theory, 1 out of 10 of those species, 19 or so, 18, 19, would be considered nuisance or harmful, meaning that they would have some economic or ecological impact. Even if you term them nuisance, the best case scenario, the impacts would still be minimal, or you can control them. The worst case is you have a loss of biodiversity. As a biologist, I'd like to predict the system. People ask me all the time, well, what's going to happen if this species X get in? And a lot of times I say, I don't know. We're in uncharted territory. Here's with the Asian carp as a perfect example. And the worst case also is management or control is not possible. A paper by Ed Mills listed the species that had the greatest impact on the Great Lakes. Another paper added the rainbow smelt and the round goby to that list. And I added a few more: the spiny water flea, the quagga mussel, the fishhook water flea, VHS, the virus that's leading to fish kill-offs. So we have roughly 18 or 19. Of these, I can't talk about impacts and how we're dealing with all of these. in my mind, the three worst, of course, the sea lamprey, the alewife, and the dry-seeded mussels. We'll lump them together, zebra mussels and quagga mussels. Sea lamprey, of course, you all know the story. Came in through the Erie Canal. It was in Lake Ontario for a long time. When they improved the Welland Canal in 1920, this allowed the sea lamprey to move into all the Great Lakes. And basically, the native lake trout, which was the top predator in the Great Lakes at the time, declined. And there's restoration efforts now trying to bring it back, but you know, it's still a struggle. Alewife, many of you around on Lake Michigan in the 1960s, every spring you would have a major die-off of alewife. The other species that has a major impact in my mind are the zebra mussels and the quagga mussels. Zebra mussels, quagga mussels, and many of you don't know that there's a variant of a quagga mussel profunda, and this is the only quagga mussel that you get throughout Lake Michigan. You get some of these shallow morph quagga mussels here in Grand Traverse Bay, but this is the guy that's causing all the problems we're seeing now. And I'll kind of go quickly through some of the problems that we're seeing in terms of the ecology, particularly of Lake Michigan, but also applicable to Lake Huron and Lake Ontario as well. All kinds of changes, as I mentioned earlier. And I don't want to go through all of these, but rest assured that all aspects of the ecosystems are affected by what mussels are doing. But not only are they affecting the ecosystem, of course, when they came in, they led to major water crisis, particularly in the city of Monroe, that led to water crisis. The mussels filled the inside of the water pipes. The pipes are miles and miles long, and over time, they close them down. So this was the outrage that led to the passage of the 1990 Aquatic Species Control Act. People were scared to death that mussels were going to affect their water supplies, and they would if something wasn't being done. This is a shot from the Monroe plant in Detroit, the DTE energy plant in Detroit. So we've controlled. Basically, the sea lamprey, every year we spend $19 million putting in lampricide, electric weirs, male sterilization. We control the alewife by stocking salmon. And this was a win-win situation. We're controlling the alewife, and salmon have contributed to a $7 billion sport fishing industry. We control drycenids, or mussels, at the water intakes, at the power structures, the chlorination, biocides, mechanical cleaning. It costs $18 million a year, but we're doing it. What we cannot do, as we have done for the alewife and the sea lamprey, is control the mussels in the open environment. How are you to control mussels at 200, 300 feet in Lake Michigan? You cannot do it. So what have mussels done? As I mentioned, all aspects have been changed. These are the major changes that we're seeing. Promote blooms of the toxic cyanobacteria, mainly Microcystis. This mostly occurs in western Lake Erie, Saginaw Bay, and Green Bay. They've led to just a clearing of the water, has led to promotion of algae, benthic algae, the Cladophora. This is the scum that you see washed up on the beaches. This is what I've been mostly involved with in the offshore waters of Lake Michigan, looking at changes as a result of the spring diatom bloom. Every spring there's a bloom of good algae called diatoms, which are food for all the invertebrates which fish feed on, the prey fish leading up to the major predators, the piscivores. As a result of the loss of this bloom, we think that it's affecting many native species. And I've been mainly concerned with one, and I'll talk a little bit more about it, that's having a dramatic impact throughout the Great Lakes, I think. But anyway, here's some shots of blooms. Patrick showed some, mainly occurred in western Lake Erie. A lot of it's due to nutrient runoff, but a lot of it is because mussels are filtering the good algae and spitting the bad algae like this out. So there's no competition for the bad algae, like the microcystis, for nutrients. So they bloom when the temperatures are right. This is some of our work of trends in zebra mussels in Lake Michigan. We sample at 130 sites every 5 years, beginning in the mid-90s. When you go out there, last time we sampled was 2010. The only place we got mussels is right here off Grand Traverse Bay, and there were just a couple of them there. The rest of them, quagga mussels. So as zebra mussels have gone down, quagga mussels have gone up. And mind you, when you looked at this map here, there's no, even at their peak, there were no zebra mussels in the open waters of Lake Michigan greater than 50 meters or 150 feet. They just do not like the cold temperatures out there. Quagga mussels love it. They're all over the place. I got some video I can show later if people are interested of a ROV skimming along the bottom of Lake Michigan that just, it's impressive. All you see is a carpet of mussels. Anyway, when you talk about numbers, the peak of zebra mussels occurred in 2000, the maximum in areas close to shore, less than 2,000. Look at what we're having now for quagga mussels. And what's troublesome is while these numbers seem to be stabilizing, the numbers in deeper water are still going up. When you think about it, most of the area of Lake Michigan is deep. It's greater than 90 meters. This is a trend of quagga mussels, 30 to 90 meters in Lake Michigan, the blue, Lake Ontario, and Lake Huron. You can see there's more mussels in Lake Michigan than anywhere else in the Great Lakes. And that includes Lake Erie. Lake Erie, of course, it doesn't reach 90-meter depths, but Lake Erie falls right along here. I'm not sure why the numbers are so low in Lake Huron. We sampled again in 12, so we'll get an update of this graph about here to see if the mussels in Lake Huron are still low. And we're sampling this year to see if Lake Ontario is still going down. So it looks like, based on our latest numbers, the numbers of quagga mussels are seeming to stabilize. At least they're not going up exponentially as they did in the past. However, this is what it looks like in the bottom of Lake Michigan now. This shot was taken from the video I mentioned. You look out, just a carpet of mussels. And these are siphons. Siphons are longer than the shell length of the mussel itself. You can see them, well, maybe you can't. Here's a mussel here. Here's its siphon extended. So what this does is allow the mussels to colonize soft sediments where you have a lot of clay and silt particles right at the sediment water interface. The mussels could extend that siphon above that layer and filter the fresh material coming down. The diatom bloom. Offshore waters in Lake Michigan. This is some monitoring work that we did off of Muskegon, Gary Fonsdale and company. We have a field station up in Muskegon, so we go out with the ship pretty regularly over a number of years on a seasonal basis. This is the spring diatom bloom here. Pre-zebra mussels, quagga mussels. This is post-zebra mussels. Not much of a change at all. Ever since quagga mussels expanded in early 2000s, this is what happened. It's basically all gone. And as I said, this is key as food raining down for invertebrates that live at the bottom sediments. Water clarity, Lake Michigan. We measure water clarity by dropping a Secchi disc. And all you do is lower it down so you can't see it anymore, and you record the depth. So the deeper it is, the clearer the water. Here's the Secchi depth before really zebra mussels and quagga mussels expanded. Here's with zebra mussels, here's with quagga mussels. So the water clarity of Lake Michigan has doubled since quagga mussels have spread throughout the lake. People talk about Cladophora washing up on the beaches. That increased water clear is a direct result of that increased light. Water's clear, light penetrates down to the bottom, to allow Cladophora to bloom. Not only do they do well with increased light, they're utilizing the nutrients that are being put out by the mussels. Of course, when they're filtering, they're assimilating material and excreting nutrients during the assimilation process. Cladophora love the phosphorus that's being ejected by the mussels. Probably these are similar scenes around Lake Michigan up north here, but this is fouling of Cladophora on the western shore in Wisconsin. It's a macroalgae that attaches to the substrate, the hard substrate. It dies back when temperatures rise in July and August, and waves wash it up on the shoreline. It creates a stinking, rotten mess. I've been concerned with this native species. This species is a benthic vertebrate that lives in the bottom of all the Great Lakes except the shallower areas, not found in Green Bay, not found in Saginaw Bay, Lake St. Clair, Western Lake Erie, but very abundant in a keystone species in all the rest of the Great Lakes. The key is it has a high lipid content. It's very rich in calories, and fish love it. All this orange material, that's all lipids, fat. When a fish feeds on it, it gets an energy-rich food source. This is what's happened to Diaperia in Lake Michigan. Ever since quagga mussels expanded, look at the drop in Diaperia. Basically, when we did our survey in 10, we only found a small pocket right here. The rest of it was darn rare. The trend in Diaperia in Lake Michigan compared to the other lakes, no difference, the drop. What's curious about this is that the drop in Lake Huron, remember, mussels weren't very abundant in Lake Huron compared to Lake Michigan, but yet Diaperia dropped just as badly. Besides doing a survey every 5 years, we sample every year in the southern end. The red is Diaperia, the blue are quagga mussels, the black are zebra mussels. Diaperia started dropping even before zebra mussels became abundant, even before quagga mussels became abundant. So something, and I spent the last 15 years of my career trying to figure this out, believe me. Diaperia is declining, but we don't know exactly what that negative relationship is to the mussels. Whatever it is, it's incredibly sensitive. And if we would see mussels at 30 meters in Lake Michigan, Diaperia would collapse to zero at 50 meters. When mussels expanded to 50 meters, they would collapse at 80 meters. Diaperia would expand 80 meters, Diaperia would be gone at 120 meters. So something that the mussels were doing was remotely affecting Diaperia. The problem is there's a lot of fish that feed on Diaperia. One of these is the commercial lake whitefish. Maybe 70% of adult whitefish feed on Diaperia. It's a bottom-feeding fish. This is the condition, or condition just measures the plumpness of a whitefish, how fat it is compared to its length. Note that this was done off of Muskegon. Note that Diaperia started declining in the mid-90s. Look at the condition of lake whitefish over that same period of time. This is a healthy lake whitefish. This is a lake fish in many cases that we see now. This is just reflects what we call the dropping condition. It's skinnier compared to its length. Alewife condition, a lot of people are concerned about alewife. Now here this is an invasive species that we were concerned about having too many of them. Now worry about not having enough of them, right? To support the salmon fishery, the state's cutting back stocking rates because there's nothing for them to feed on. And the primary food of these salmon are alewife. This is condition. The alewife are skinnier, but more importantly, look at the prey fish that have gone down, including alewife. The sculpin, the smelt, the bloater, or the bloater chub, in addition to alewife, have all gone down. The mass of these prey fish that many of these piscivores feed on is at historical lows at this point. When you look at biomass, or just the mass, don't think about numbers, think about tissue, mass out there now. This is what we had in the mid-90s. Diapry was still present, and just about as many mussels as in terms of mass as there were diapry. This is what we have now. But what is impressive about this is this increase here. Most of this mass, 40 to 50%, is shell. All right, this is shell and tissue. A fish can feed on a mussel, and they do, but half of that food that they take in is shell, which has no nutritional value whatsoever. So not only does the fish spend energy getting the mussel and breaking or separating the meat from the shell, it has to pass the shell. And in many cases, the fish thinks it's full, which it is, but it's full of material that has no nutritional value. It's filled with shell. And there's energetic cost for the mussel to produce that shell. 40% of the energy that the mussels take in goes to build that shell, which is lost. It's washed up on the beach, right? That's energy that's lost to the system. This is the mass of mussels compared to the mass of prey fish. Prey fish is alewife and all those other species I mentioned. This is the mass of mussels out there now compared to those fish. It's incredible. What we're doing now is trading muscle mass on the bottom, which goes nowhere, when we had now, and compared to a diapria, which fish fed on, which moved or cycled the energy from the bottom back up to the food web. Now basically is a dead end. As I mentioned earlier, people ask me all the time, well, can we predict what's going to happen? In this case with mussels. In certain cases, we could. When we went out, when mussels first became abundant, we looked at the European literature because mussels, zebra mussels particularly, are not new. They're new to North America, but not new to Europe. There's been tons of studies done. And we knew that when zebra mussels got in and quagga mussels got in, we would see an increase in water clarity and a drop in chlorophyll. We would see that we would increase in plants. One thing I didn't talk about, we've lost, or in danger of losing completely in the open waters, 30 or 40 species of native mussels, or what we call unionids. We did a study of the change in Lake St. Clair of species of native mussels before we happened to be at the right place and right time, and we did a survey of mussels before zebra mussels got in. There were 20 species in the open waters. Now there's nothing. It's all completely zebra mussels or quagga mussels. So we could have predicted that would happen here in North America. What we could not predict was the loss of diapria. It's unprecedented. You don't see anything like this in Europe. It's one of those species that's kind of unique to large lakes, and particularly the Great Lakes. This is a native species that's been around since the glaciers receded. We could not have predicted quagga mussels getting into deeper water. In fact, that profundomorph of quagga mussels, when I asked people, particularly Russian colleagues, have they seen this profundomorph, they had no clue. They had no clue that that potentially this profundomorph could expand into deep waters as it has in the Great Lakes. Avian botulism, we could not have predicted that based on the European literature. And the promotion of microcystis blooms, we could not have predicted that at all. So I guess in ending, what I'm saying is that although we have some sense of what may happen when the species get in, we really don't know. It's really tough to predict. There are consequences of invasive species that are direct as well as indirect, and everything's connected, and one thing leads to another. So if you ask what impact Asian carp are going to have in the Great Lakes, that's really a tough call. we know what's happened in the Illinois River and other places where it's become abundant, but when it reaches the Great Lakes and nearshore areas and some of these river systems, what ecological impact they're going to have, it's really tough. That's hard for me as a biologist when a reporter asks me, well, what do you think is going to happen? I hate to put my foot in my mouth. When you go back, if I say something 5 years later, it doesn't turn out to happen. So I'm always cautious about that. And it's the unpredictability of what's going to happen. I think that's the key when you get these. So the key is prevent them from coming in the first place. That's the key. In some sense, we have with ballast water regulations. But there's other species that are waiting to get in Europe that, one thing that alerted me was the killer shrimp. It's feeding on invertebrates in European rivers and nearshore areas, and if that thing gets in, the equation changes again with another invasive species. So with that, I think I'm out of time. So thanks for listening, and next time you see mussel shells on the beach, remember that's wasted energy. That's energy that's not available to fish, okay?